new things are being covered, so many sophisticated things too. So, in comparison, what I am presenting seems pretty lowbrow, apart from being very old. But I think this is a foundation in a sense, and if it is understood and taught better, well and good. So, let me hope I am making some useful contribution. Now, what I want to do today is cover 2 or 3 important aspects. The first one is to describe, sketch the group properties of the set of all canonical transformations on a given phase space. I want to repeat the thing which I keep saying so often, that physicists use the word canonical transformation in a somewhat informal or loose way. The passage from a set of generalized coordinate and momentum variables to the action angle variables is called a canonical transformation. But we must understand it does not have a geometrical meaning of being a map of phase space onto itself. I said it yesterday, I repeat it now. In quantum mechanics, somehow we are a little more careful. Suppose you want to solve the Schrodinger equation for the 3-dimensional hydrogen atom problem, you may first write the Schrodinger equation in Cartesian variables, right, x, y, and z. Then you realize, because the potential is spherically symmetric, the equation will be much easier to solve if you use spherical polar coordinates. But nobody will say the passage from Cartesian coordinates to spherical polar coordinates is a unitary transformation. No one will say that. So, we are by nature more careful, I think, in quantum mechanics than we are in classical mechanics in this respect. All right. Now, you have also seen, and it will become more and more clear as we proceed, that the concept of phase space is really very profound, because it brings up many geometrical properties which have no meaning at the level of configuration space. And in a sense, this was the great value of Hamilton's discovery, though he was not the one who brought it all out. It was Jacobi mainly who exposed the geometrical properties. So, what I will do is to sketch the group properties of the set of all canonical transformations on a phase space, and for this purpose I will use the definition of a canonical transformation, the number 2 which I gave, which is extremely compact and very easy to handle. It is not explicitly stated in terms of Poisson brackets, but it amounts to the same. I will just write this in simplified notation. A summation of the various degrees of freedom is understood, and a transformation in phase space, a mapping, let me say, of phase space onto itself given by some set of functions q prime p prime, is a canonical transformation if and only if the differential expression p prime dq prime minus p dq is the exact thing. It is the differential of something. So, this is a very nice handy definition of a canonical transformation. I want to emphasize this definition is completely equivalent to the one I stated first yesterday, namely the Poisson brackets among the fundamental variables must maintain their values. So, it is a nice exercise for you to convince yourself this very compact statement is the same as that. Now, I can use this to point out the important properties of canonical transformations. First statement is, much of it I can say orally. suppose you make no change at all, suppose q prime equals q and p prime equals p. Is this condition satisfied? Of course, the left hand side is 0, it is exact, it is d of 0 or d of 1 or any number. So, the identity transformation, identity mapping on phase space is of course a canonical transformation. Now, of course, it is understood that when a mapping is given in this way, it should be invertible. You start by writing q prime as a function of q and p, p prime as a function of q and p, and from those equations by algebraic operations, it is understood that we will be able to write q in terms of q prime p prime, p in terms of q prime p prime. That will be the inverse transformation. Is that also a canonical transformation? Can you tell me from here? The passage from q prime p prime to q p, is it canonical? Yes, just the change of sign. So, you see how handy this definition is. You do not have to go on checking some n squared or odd Poisson brackets, just look at this and it is done. So, the inverse of a canonical transformation is canonical. And now, let me suppose that we make a second transformation mapping q prime p prime to q double p double, and let us suppose that also is canonical. So, what it means, p double d q double minus p single q single is the d of something, I will call it S prime. So, what about the composed mapping going directly from q p in phase space to the point q double p double? Is this canonical? Obviously, just add these two things. Okay. So, it is p double q d q double minus p d q is also exact. So, I hope you are really impressed with this definition of a canonical transformation. It makes it so easy to convince yourself that that the set of all canonical mappings of a phase space onto itself is a group. Of course, there is an infinite group, there are any number of elements of it. Okay. Now, if you like, you can consider canonical mappings which have an explicit time dependence, but for simplicity generally I will avoid that. The equations get just a little bit more involved. For the case of non time dependent, that is, for the case of canonical transformations which do not carry any time dependence, what is the meaning of a canonical transformation? If you start with any Hamiltonian in the variables q and p and write those Hamiltonian equations of motion, and now you switch to q prime p prime, you are guaranteed there will be a Hamiltonian in terms of q prime and p prime, and the equations of motion can be written in the new variables, they have the same Hamiltonian structure. All this is, that is the meaning of a canonical transformation. For a time independent, I mean for a canonical mapping which has no explicit time dependence, the rule to construct the new Hamiltonian H prime in terms of q prime p prime is just this. It just preserves the values of the Hamiltonian point by point in phase space. Okay. Yeah, somebody had a question? No. Okay. Now, to get an even better feeling for this set of all canonical transformations, maybe I just write draw a diagram. This is my phase space based on a configuration space capital Q. From configuration space Q, I go to the corresponding phase space. So, here is a point Q p under a canonical mapping, canonical transformation, it is carried by the transformation to an image point Q prime P prime. Here are some simple simple subgroups of this large group. I want to repeat that the set of all canonical transformations on the phase space as a group, it is much larger than the set of all point transformations of capital Q onto itself. It's much larger. Okay? And you will see in a moment examples of that. Of course, if you have a point transformation, which is to say, in this transition, the new coordinates are functions only of the old coordinates, then it automatically can be jacked up or extended to be a canonical transformation. I have given this equation earlier. Which way does it go? When you make any point transformation on configuration space, a mapping of capital Q onto itself, you can extend it to become a canonical transformation on the phase space in this way, and you can see that the characteristic here is that the momentum variables transform linearly. Okay? That is an interesting property of this thing. And so it is a canonical transformation, and for this case, what is the value of that function S? What is this S in the case of a point transformation raised to the level of a canonical transformation? Look at the way I have written P prime in terms of P. So what is P prime R dq prime R? It is Ps dqs, isn't it? So S is 0. This differential expression is the right hand side is 0. So it obviously satisfies the condition to be a canonical transformation. So point transformations are particular cases of canonical transformations. They have the property, the momentum, the coordinates transformation do not involve momentum variables. The momentum variables transform linearly. These are the two important properties, and this S happens to be 0. So this is the case of point transformations. So this, you say, is a subgroup of the group of all canonical transformations. So I repeat for clarity, the Lagrangian system of equations of motion preserves their form under point transformations. When you go to the Hamiltonian version, that property will remain. Point transformations which preserve Lagrange's equations will also preserve Hamilton's equations. By that time, they have become canonical transformations by this definition. Okay? That part is obvious. But now there are many more possible canonical transformations, many more beyond this. One is a family of transformations called contact transformations. These are all those canonical transformations for which the function S can be taken to be 0. That is, P prime dq prime equals P dq. Now you might think, isn't this what we just saw? Of course, point transformations are examples of contact, but the contact transformations are much larger. All right? And you can work out the most general form of contact transformations. So let me say like this. You have the set of all canonical transformations. You have the set of all point transformations, and the contact transformations lie somewhere here. So how is the inclusion? It goes like this. You can see a chain of subgroups. So the interesting characteristic property of this contact transformation idea is the following. It differs, in general, it differs from point transformation in this way. Let me write the equations and then describe them. The most general contact transformation is one in which S is 0 and it is a consequence of S being 0. This is something you can derive, a little bit of playing around with calculus. In a contact transformation, in general, the coordinates depend on the momenta in a linear, in a way which is homogeneous of degree 0. What does it mean? Basically, it means the coordinates, the new coordinates, are allowed to depend on the momentum. Here, that was not so. But they depend basically on the ratios of the momentum variables. It's homogeneous of degree 0 in momentum. Here, it was independent of momentum. So, you can have other transformations in this class which are not point, and this will be their property. The momentum, however, will remain homogeneous of degree 1. Okay? So, here it was explicitly linear. It is homogeneous of degree 1, but here you can have expressions, just for example, of P1 squared divided by P2, just as an example. Such a term can appear. It might be there in a contact transformation. So, I hope you see point transformations do have S equal to 0, but there are others also which have S equal to 0. Set of all canonical transformations with S equal to 0 is a well defined class. These are the contact transformations, and the characteristic property is they are homogeneous in momentum variables of degree 0 here and of degree 1 here. That is true in the point. It is explicitly verified in the upper case. Okay. The third one I will describe. It has shades of quantum mechanics in it. That is why I want to explicitly mention it. I will call it phase transformations. These are transformations in which the S in the defining equation, which I have just rubbed out, is a function of the coordinates alone. And so, now I will put all the indices here. The coordinates q's do not at all change. The momenta change in the way I am now writing. Take any function S of the coordinates alone, then this is a canonical transformation. It is a simple exercise for you to confirm that this obeys all the Poisson bracket conditions. Of course, it obeys our defining P prime dq prime minus P dq equals ds, but you see the shape of it. Coordinates do not change, momenta shift by gradient. This is exactly what happens in Maxwell theory gauge transformation, same spirit. So, that is why I call them phase transformations. Okay. So, clearly these transformations are not of this type. They are not of this type. They do not do anything on the configuration space. They affect only the momentum. In quantum mechanics, when do we see this kind of thing happening? When you take a wave function psi of q and multiply it by a phase factor dependent on q. That is exactly what happens in Schrodinger wave mechanics. So, you see shades of it already at the classical level. That phase transformation is not of this type either, because S is not 0. That is all you have to notice, nothing more. Okay. So, this is nice. Now, the last comment, there is one more, but before coming to that, I want to make a statement that in general, when you consider an arbitrary canonical transformation, the variables q prime are functions of all the old q's and p's. So, what it means is that under a general canonical transformation, the configuration space idea is lost. You have to look at the transformation as a whole. It is a beast, enormous thing, affecting or changing every q and every p in such a way that they can all get scrambled up. Okay. Now, this is very easy to see. Well, okay, we will see examples later, but I just want you to say, to realize the concept of configuration space is not preserved under a general canonical transformation. If you have a point transformation, yes, it is preserved. But if you have a contact transformation which is not of the point type, no, the q, just this capital Q space, it has no special significance, it disappears. Okay? So, you must realize that this is so. So, this emphasizes that in Hamiltonian description of motion in this machinery, we really seriously must think of coordinate q and momentum p as being on the same footing. You cannot separate q from p and give it some special significance. Okay? After the canonical transformation, the new q may depend on the old q and the old p, and that is all that I am saying. Okay. The last one I will describe is physically quite important. I want to show you what is the shape, what is the structure of an infinitesimal canonical transformation. What do I mean by this? I imagine the canonical transformation, this mapping, to be of the following kind. Every q prime shall be equal to the corresponding q plus a small addition. Every p prime shall be the old p plus a small addition. So, I ask, if I have a canonical transformation of this form, the changes in q and p going to q prime and p prime will be written as delta q r and delta p r. We will think of these as quantities of small quantities of the first order, and in all calculations we retain only first order quantities, first order terms. So, delta q1, delta q2, each of those is some function of qp, but it is to be thought of as small quantity of the first order. Similarly, delta p1, delta p2 and so on. Now, you impose the condition that this should be a canonical transformation. You can use any definition you like, definition 1 in terms of Poisson brackets, or definition 2 in terms of the exactness of that expression, and so on. And it is a little bit of work, which is, I think you will be happy to get this answer. Every such transformation necessarily has the form I am now writing. I am repeating that we keep only terms up to first order in these small quantities delta q, delta p, and the condition that this should be a canonical transformation turns out to be the following. Every delta q must be the Poisson bracket of that q with some infinitesimal function g of q, delta g of qp. I write delta because I want to keep track, first order terms only. Every delta p must be the Poisson bracket of that p with that same delta g. Okay?
Even though we are writing delta q, it is not q in strict sense.
Beg your pardon?
We are writing delta q. Okay?
Yes, yes.
But it is not
each, it is like this.
It is not the small change in Q only.
Yeah, the change in Q is something which can depend on all the Q's and P's. If you like, I could do it in this way, but I didn't want to for the following. I could write explicitly some small parameter epsilon and then say it is some function of Q and P. Similarly, I could say I am considering transformations in which the P's are also delta P's, the changes are proportional to some common small parameter and then some functions of QP. But I am putting all of it together without separating it to epsilon. You have to imagine it is there. So I just say it in words that we imagine an infinitesimal canonical transformation. Each point QP is mapped into a nearby point. That nearby point, its coordinates can depend on QP. Its Q can depend on QP, its P can depend on QP. Then you check what are the restrictions on delta Q's and delta P's coming from the requirement that this be a canonical transformation. The answer is what I have written. Every delta Q must be the Poisson bracket of that Q with some function, infinitesimal function, and delta P must be of this kind. Yeah, one single function. So, an infinitesimal canonical transformation is completely determined by one infinitesimal function of phase space. It is called the infinitesimal generator of this canonical transformation. So, delta G is called the infinitesimal generator. Of this canonical transformation. Okay? So, I hope you are really impressed by this. In this sense, the Poisson bracket initially was used as a way to define what we mean by a canonical transformation. Lo and behold, now it is allowing us to construct such transformations. The transformation itself is built up using Poisson bracket operation. Okay?
So every generator can generate a canonical transformation, or the canonical transformation can generate the generator?
No, it's one way. Leaving aside global questions and so on, any infinitesimal function of QP in principle gives rise to an infinitesimal canonical transformation. Okay? So, for every infinitesimal canonical transformation, there is an infinitesimal generating function, infinitesimal generator. The point is that that is just a real valued function on the phase space. It is first order, it is infinitesimal, that you have to proportional to the epsilon which I rubbed out. Apart from that, loosely speaking, you can choose any function on phase space, make sure it is a small quantity, put it into these Poisson bracket expressions, the result will be a canonical transformation, but it will be infinitesimal, close to the trivial transform, close to the identity. I hope this is clear. Now, can you tell me, very simple question, will different delta G's give me different canonical transformations by this construction? Is there a choice of delta G in which the transformation is identity? Nothing at all. Constants. If delta G is shifted by a constant, no change in the transformation. So, it goes one way. Every infinitesimal generator gives the corresponding infinitesimal canonical transformation, but the reverse, given the infinitesimal canonical transformation, its infinitesimal generator is determined up to an additive constant. Okay? These are quite subtle and nice features. All of these things have their mirror statements in quantum mechanics. I will not go into it now, but I want to bring these out and you should look for them. Okay. So, now you can ask the next question. Suppose I have a function, some arbitrary function on phase space. By how much is it altered by such an infinitesimal canonical transformation? The change in every q is given here. The change in every p is given here. For these changes, delta qr, delta pr, how much change is there in a function given which you choose? It's very easy to calculate. The change in any function of phase space under this infinitesimal transformation is the Poisson bracket of that function with the infinitesimal generator, delta g. I hope you are with me up to this point. Now comes a beautiful application of this. I must say this quality of this green board is really fantastic. It's such a pleasure to write and to rub also. In most places, especially if they are new, it is a pain to rub out. No? But this, I think adequate use has made them like this. Really. Maybe. Special glass, I think. The use also makes it like that. Now, suppose you look at a given Hamiltonian and you have the Hamiltonian equations of motion. We have seen that they are given the equations of motion. These are the Hamiltonian equations of motion. All right. So, now here you are in phase space at time t, and then you want to go from time t to a nearby instant of time. That's what the Hamiltonian equations of motion are supposed to tell you. So, let me call this these changes, let this change be delta q and let this change be delta p. So, somebody kindly dictate to me the change in a q because of the equations of motion in a small time delta t. What is it? Here is qr dot dq by dt. So, how much is the change for time delta t? Somebody tell me. It's not complicated. No trick. Yes? Come on. Yes, please. Poisson bracket of what with what? Yeah? Very good. Continue. QR with what? Huh? That's all? Yes? Something else? Huh? Delta t. Oh, very good. And since you have done this, I have the strength to do the next one myself. The changes in coordinates and momenta obeying Hamilton's equations of motion in a small time delta t are brackets of q and p respectively with delta t times the Hamiltonian. All right? Now, please compare that with this. What does it tell you? Yeah, make a statement. What do you learn comparing right with left? What can you say about these delta q's and delta p's? So, first statement, the changes in q's and p's on phase space in a small time delta t are the action of an infinitesimal canonical transformation. The change in time is a canonical transformation. Do you understand, right? And the generator of that transformation is Mr. Hamilton with the delta t, because it has to be infinitesimal. This is one of the very beautiful results of this entire framework of mechanics. So, it means, for example, if you take a finite stretch of time from q of t1 and p of t1 to q of t2 and p of t2 finitely later, let us say, then you can break it up into a lot of infinitesimal pieces, lot of delta t's, all right. In each delta t, the motion in the phase space is given by an infinitesimal canonical transformation, right. But canonical transformations are a group. So, you compose all of these one after the other, one after the other. The end result is a finite canonical transformation, all right. So, what do you see? That if you had been able to solve Hamilton's equations of motion and express q's and p's at a later time as functions of q's and p's at an earlier time, those equations would be the equations of some canonical transformation. So, statement: evolution in phase space according to Hamilton's equations of motion are said to be a, this is a standard phrase, continuous unfolding of a family of canonical transformations. I do not have to write it, I have said it. So, it is true. All right. So, the whole idea of development in time in Hamiltonian mechanics becomes a continuous family of canonical transformations acting little bit at a time, little bit at a time. Okay. So, it also means that well, for this family, H is the infinitesimal generator in the language I have used here. All right. So, I hope you find this. I know the subject is very old and so on, but it has so much of beautiful structure. All right. So, now so this is called the gradual unfolding theorem, something like that. And in quantum mechanics, the Schrodinger equation, it becomes a statement that time development in quantum mechanics following the Schrodinger equation is a continuous unfolding of a unitary transformation, which is generated by the Hamiltonian as an operator. Okay. So, you see how much parallels are there. Okay. So, at this point, I will, oh boy, I thought time is going infinitesimally, but it is not true. So, I will write two important statements which summarize what I have said and then go on to the next topic. Statement 1, I mean, I have said this in many ways, but I want to emphasize it. Any system of Hamiltonian equations of motion retains its Hamiltonian form under any canonical transformation and a suitable new Hamiltonian can be defined, This is first statement. So there's nothing new, but I just want to focus on it, on the statement. So in this way, the set of all canonical transformations on a phase space has an independent existence and meaning, whatever may be the Hamiltonian you happen to choose for your dynamical system. Whatever Hamiltonian you choose, whenever you make a canonical transformation, you will be able to define a new Hamiltonian for that system. This is statement 1. Statement B, for a given Hamiltonian, the solution to the Hamiltonian equations of motion express Qt2 Pt2 in terms of Qt1 Pt1 as a canonical transformation for each choice of T1 and T2. I mean, over any time interval, the result of the evolution is some canonical transformation, and we call H is the infinitesimal generator of this family of canonical transformations. That's the way in which the Hamiltonian plays a role. Okay. So I hope you get an overall picture of canonical transformation idea, and now I can list the 3 different ways in which we can construct or express or describe a canonical transformation. Again, it is repetition of what we have seen already, but it is good to periodically collect our thoughts. For our purposes, canonical transformations can be, I will just say, handled in 3 ways, and in any given situation you use whatever is most convenient. First method, fully explicit. A system of 2n equations giving every q prime as a function of qp, every p prime as a function of q. Okay. So this would be the brute force, if you like. This is the first method. Second method, implicitly via a generating function, which is something I introduced yesterday. For example, of the form this is an implicit way of describing or specifying a canonical transformation. You say its generating function is such and such function s of q prime and q, old coordinates and new coordinates, and the momenta are given in this way. Of course, we know that there may be canonical transformations for which this kind of description is not possible, but we don't have to worry. We have this beautiful Carathéodory theorem. If not one, there will be another, many others. Okay, so this is an important thing. And now you have to be very careful. The idea of a generating function in this sense is is separate or different from idea of infinitesimal generator. The two are not the same. A generating function is an implicit way of describing a finite canonical transformation in one shot. Okay? An infinitesimal generator is something which builds up a canonical transformation incrementally through a differential equation. Therefore, that brings us to the third way of building up canonical transformations via a system of what you can call Hamiltonian equations of motion in quotation mark. It may not be the actual dynamics, but it is possible in principle to take any function on phase space, put it into Hamilton's equations, thinking that it is a Hamiltonian, solve those equations, the result will be a canonical transformation. So, implicitly via a system of Hamiltonian equations of motion using an infinitesimal generator. Okay. So, just keep in mind there are these three different ways in which it can be done. Okay. So, this is the first topic I wanted to cover today. Now, I go on to the second one, which is actually again it is a beautiful result in classical mechanics, Hamiltonian mechanics. I hope all of this gives you some joy also. And they are so beautiful, these results. The pity is that they have some limited validity. I mean, at a very fundamental level, I think the world is Hamiltonian. But if you have to describe a more physically realistic dynamical system, it may be non-Hamiltonian when you have to include various other effects. Just as in quantum mechanics, just aside, we always think of the Schrodinger equation as the fundamental equation of motion in quantum mechanics involving a Hamiltonian operator. But these days, people have realized whenever you are looking at the dynamics of a quantum system, you must always keep in mind that it may be interacting with its environment. The Schrodinger equation describes only the dynamics of an isolated quantum system. If you want to take in the interaction with its environment, you have to go beyond the Schrodinger equation. So, in that spirit, I think here also you have to go beyond, as Shamik said, Hamiltonian systems are a very small part of set of all dynamical systems, and we have to pay attention to the whole set. Okay. In the quantum mechanics case, the generalization of the Schrodinger equation for the situation I described where the effects of environment are included, this was an effort you should all be interested, which was begun by Sudarshan in 1961. But it is such a demanding problem. He and two co-authors, P.M. Matthews, who was, you know who? Vice Chancellor Maharaj's PhD guide, P.M. Matthews, and a third person, Jayasita Rao. They wrote a paper in Physical Review, Stochastic Dynamics of something something. I have a copy here. So, that was a starting point, how to go beyond the Schrodinger equation in quantum mechanics. But it turned out that problem involves extremely subtle mathematical features which they had not realized at that stage. They took the first steps in that direction, and then many others came and made contributions. Gorini, Kosakowski, Lindblad, and Krauss, these are the various names. But the starting point was Sudarshan and his collaborators, today it is called the Gorini, Kosakowski, Lindblad, Sudarshan master equation. That is the most general equation of motion in quantum mechanics for a system which is not a closed quantum system, and that is very much in use in many fields of research today. Okay. So, in that spirit I am saying Hamiltonian classical dynamics is in that sense very small part of the real world, but you must understand this well. Many of these features will not survive when you go to a general dynamical system, but doesn't matter, you still pay attention to it and learn it. So now I come to the next topic. It's a small set of ideas, but again extremely pretty. Now this is the role for the action of a Hamiltonian system as a function. You will find this really quite, it's really beautiful. You remember I wrote once the expression for the variation of the action function for a given Lagrangian system. The action which we used in Hamilton's principle is the time integral of the Lagrangian, and it is called a functional, because you can choose any trajectory, if you like, in the configuration space, going from given initial time and initial q to some final time and final q. So maybe I write q2, q1. Configuration q1 at time t1 is given, q2 at t2 is given. You just draw some smooth path connecting one to the other. You can calculate this, this action functional. Do you remember the expression for the change of this action functional? If you make a small change in this path C plus small changes in the endpoints. Remember the expression. It would be nice if I will write the part which is easy. This is the contribution which comes from the body of the integral. And then there are some boundary terms. Can you go back to your notes and dictate the boundary terms? Huh? Yeah, any? PR delta QR, but so and they are taken at the initial and final times. So tell me the T2 contribution and then the T1 contribution. So what are these terms? The T2 contribution, the P delta Q. P PR of T2, T2 and then the other part minus, yeah, EL for us now it is the Hamiltonian. Is this correct? And then one more term. Remember, recognize all these terms. Earlier I had just written these boundary terms as a square bracket, something inside at T2 minus at T1. So I have written everything out. All right? Okay. Now we exploit this result in a very nice way. We can draw a simple picture. Here is Q at time t1 and here is Q configuration at time t2. And in this expression, in this action functional, I had in mind any choice of a trajectory in configuration space starting here and ending there, and I called it C. All right. Now, suppose you choose for C the actual path followed by the system obeying the equations of motion. All right. So, I will call that the dynamical path given q1 t1 and q2 t2. In general, I mean, provided some reasonable conditions are satisfied, if you give me q1 at time t1 and q2 at time t2, initial and final configurations and times, in general there is a unique solution of the equations of motion which connects them, the path which the system will actually follow, obeying Newton's Lagrange's equations of motion. So, it means that phi calculated for C equal to the actual path, is it a functional or what kind of mathematical object is it? I say that C dynamical is determined by the data given at initial and final times. So, C, you give me q1 t1 and q2 t2, C dynamical is known all along from t1 to t2, the coordinates are known at each instant of time, and so if I compute my action functional for the solution of the equations of motion, what kind of object is this? Is this a functional or is it a function? It's a function. What is it a function of? What are the arguments of this function? Huh? q1, q2 and t1, t2. I will therefore use this notation for it. So, the action functional, its first role in life is to show you a way of deriving the equations of motion. That is what Hamilton's principle is designed to do. After doing that, you need not throw it away in the waste paper basket. It still has a lot of meaning and life in it. Okay? You say, go back to the action functional, calculate it for C equal to this chosen to obey the equations of motion given the initial and final conditions, and here it is. Now, for this is now not a functional, it is a function of initial and final times and configurations. So, what are the things that you can vary here? You can vary the initial time, you can vary the final time, initial configuration, final configuration. All these are independent arguments of this function S. And if now I go back to this general expression for the variation of the action functional, I calculate everything along the dynamical path. What happens in this equation? First term is gone. And what are the boundary terms telling you? I want you to see this. Look at the terms here. The change in the action as a function, which we have obtained by always obeying the equation of motion, still it is given by this. So, what is this term? It is a change in the function S if q at time t2 is varied. So, do you not see that this is by, right? This calculation of the extended action function, Hamilton's principle, is full of information. And what is P of T1? Now, do these remind you of equations which we saw a little 15, 20, 25 minutes ago and yesterday? Description of a canonical transformation, a finite canonical transformation via a generating function, which is what we saw yesterday, we saw earlier today also. All right. So, the action reduced to a function, not a functional, is the generating function for the canonical transformation, which describes development in the course of time. Okay. It was all of these things which went into the Dirac 1934 paper, the Lagrangian in quantum mechanics. It's a very famous paper. I told you on the first day, it was the inspiration for Feynman's path integral formulation of quantum mechanics. So, it's such a beautifully written paper. The title, The Lagrangian in Quantum Mechanics. The journal, in those days, Dirac had a lot of sympathy for Russia, for the communist movement in general. And there was an obscure Russian journal called Physikalische Zeitschrift des Soviet Union. And this paper was published in that journal. But it is easily accessible. There is a collection of papers on quantum electrodynamics edited by Julian Schwinger. It's a Dover book, Quantum Electrodynamics. Editor Julian Schwinger. That paper of Dirac is printed there. So, I think your library must be having it. So, so it is 1934. So, what I am telling you now is very much at the heart of what Dirac did in that paper. All of this is Hamiltonian mechanics, but he said, does the Lagrangian have a role to play in quantum mechanics? And then he put it all together, and Feynman carried it forward. Okay. So, this is, you can see that the action, when it descends from being a functional to being a function by imposing the equations of motion, it becomes the generating function of the canonical evolution. But there is a little bit more remaining in these things. We have some expressions for partial derivatives of this S with respect to T1 and T2. So, I will not write all the arguments, just tell me what is this and read off from there what is delta S by delta T2 and what is delta S by delta T1. Delta S by delta T2 is this one. Right? And this one is so the action, after it has performed its function of telling you what the equations of motion are, it remains, you can say, full of life. Regard it now as a function, not as a functional, and then in the finite description of the motion, this generating function tells you, if you want to go from q1 at t1 to q2 at t2, what initial velocities must you choose? In other words, what momentum should you choose at the beginning? Here it is. And when you reach q2 at t2, what will the velocities be, or what will the momentum be? It is this. And what will the energy be? To start with, it is this, and to end with, it is that. Of course, the energy is conserved for an h which does not have time dependence. Okay. So, you see, so many, you can say, goodies are coming out of this calculation of the extended Hamilton's principle.
So this capital S that can be interpreted as kind of propagator.
Yeah, if you like, I don't know in classical language how it is regarded. In terms of wave functions, definitely psi at q2 at t2 in terms of psi of q1 at t1 is written as an integral with a certain kernel inside, and that is called the propagator. And so that in the quantum fully quantum case is the coordinate space matrix element of the finite time development operator, e to the minus iht, as an operator. So basically what happens is that the quantum mechanical kernel which you are talking, a propagator, is e to the power minus I times this classical h over h bar, s over h bar, which was Planck's constant. This is what Dirac discovered and showed in that 1934 paper, that the quantum mechanical unitary development in each infinitesimal interval of time is to leading order its matrix element or the propagator or kernel is e to the power minus I classical s over h bar. This was the starting point. Okay. So that is how it is related to propagator. In Dirac's time and in his paper, the word propagator was not used. It was brought into physics by basically Feynman, that we know. Yeah, I still have some time. So now, I have done second topic for today. The first one was a description of the properties of the family of all canonical transformations, why they form a group, some interesting examples, subgroups, and all that. And now, and different ways in which to describe canonical transformations, infinitesimal ones, and so on. Then this has been an application of the infinitesimal case to the case of the action as a function. Now, this last set of equations, which are coming from this calculation of the variation of the action, this time delta t1, delta t2 contributions, this is what is called the Hamilton-Jacobi partial differential equation. Now, this is a very beautiful part of classical Hamiltonian dynamics, and some people regard the Hamilton-Jacobi equation as the most aesthetically most beautiful version of classical mechanics. It's not just my opinion, many people think so. And this Landau and Lifshitz book on mechanics, its spirit is given by the Hamilton-Jacobi view of mechanics. So this is where that comes. Now, the Hamilton-Jacobi equation itself can be derived in more than one way, motivated in more than one way. One of the ways is what was described by Shamik yesterday, trying to simplify the Hamiltonian equations of motion by choosing a suitable canonical transformation, so that in the new Hamiltonian there are only momentum variables and no coordinates. In his example, it was only action I should be in the Hamiltonian, no theta should be there. Okay? So the function k, the requirement or desire was, can we make k a function only of half the canonical variables? Then those canonical variables will all be constants of motion. The other fellows, their conjugates, will be linearly developing in time. That was the whole spirit. But so one can arrive at the Hamilton-Jacobi equation and discuss it from that point of view, and that is what is done in many of the older books. I will, well, this is a finite set of lectures. I will take this as the starting point of the Hamilton-Jacobi equation, okay, and I will tell you a little bit about it. So I will rub this board. And you look at, so there are two equations of similar nature here, the derivative with respect to final time and with respect to initial time. I will concentrate on this one. So I will write that in the following way. The Hamiltonian at time t2. Its arguments are q of t2 and p of t2. What is p of t2? Here it is. So, I will just write this is h of q2 p2. I am bringing it to the left, and then I have where here S is just a shorthand for this entire expression. Okay. So, I have just rewritten this equation, brought both terms to the left and written it in this way. And there is, as I said, a companion equation at the time t1. So now I will do the following. In this equation, you can see that the initial time and the initial position are just dummy variables. They are there as second set of arguments in S, but they are not involved in any partial differentiation or any calculus type operation. They are just there telling you where this whole equation came from. So, suppose for the moment I just ignore their presence, which means I can do something which you cannot. I can rub them out, right? So, imagine writing an equation of this kind where S is to be regarded as a function of q of t2 and time t2. Now, is it necessary to retain the subscript 2? No. You have a time and a coordinate at that time. So, I will remove this also. Okay. This is called the Hamilton-Jacobi partial differential equation. So, what are the ingredients? A Hamiltonian must be given, a function of q and p. The unknown which you are trying to solve for is a function s of q, and the equation which this s of q must satisfy is this. So, I will now rewrite this. This is the Hamilton-Jacobi partial differential equation for a given Hamiltonian, which depends on various coordinates and momentum variables. The unknown here is s of q. And so, the general mathematical question can be posed in this way: given a Hamiltonian on some phase space, can we study the existence, the construction, the description of solutions of this partial differential equation on its own? It is true that if you went to the action and you did all that we have just done, regard the action as a function derived from using the equations of motion, the action obeys this equation. But for the moment, put that out of your mind, focus on this equation standing on its own. This is called the Hamilton-Jacobi partial differential equation. And there is a lot of mathematical literature on this, generalizations of this Hamilton-Jacobi equation and so on. So, what we have seen is that the action obeys the Hamilton-Jacobi equation. Okay. Yeah. So, I will summarize some of the things which are known. I will give you only a brief description, and then I will stop for today. One thing is known to you from your study of Schrodinger wave mechanics. This equation is the leading part of the Schrodinger wave equation in the so-called WKB approximation, right. So, the Schrodinger wave equation is a perfectly well defined equation on its own. It uses wave functions on configuration space, well defined everywhere, normalizable and so on, and the Schrodinger equation, time dependent equation, describes its unitary development. This classical limit of the Schrodinger equation, leading term, however, has only a local character. I do not know if there is great deal known about the global properties, global meaning all of configuration space. Can you construct solutions of this equation which are well defined, behave reasonably all over configuration space? These are questions of a global character. I do not know any simple, easy to understand answers to these questions. So, it may be my ignorance, but I think it is also true. There is something about the Schrodinger equation which makes it very well posed. You know that if you have a Hermitian Hamiltonian potential which is reasonable and so on, the wave function, full wave function will develop unitarily, no question. That propagator is well defined. In the classical limit, the statements that one can make are unfortunately mainly of a local character. So, let me now say this. People talk about two kinds of solutions of the Hamilton-Jacobi equation. One is called a complete integral and another is called the concept of a general solution. Now, the complete integral I do not want to take up. I described it in the notes, you can read it there. So, for this actual presentation, I just want to tell you something about what is the meaning of a general solution of this Hamilton-Jacobi equation, how is it to be described. Now, you see that very much like the Schrodinger equation, this Hamilton-Jacobi equation is a partial differential equation in time of the first order, all right. Of course, the dependence on q is also partial derivatives of the first order, but I am stressing the one on the time dependence. So, one can imagine that suppose you take an initial time t0 and you choose some function on configuration space, a function little s, and you say if I want a solution of this time dependent Hamilton-Jacobi equation which at t0 starts with little s of q, can I use this in a recursive or iterative way to build up capital S at times greater than t0. Here is the first time derivative. You differentiate this once right through with d with respect to t, you will get the second time derivative and so on. So, you can in principle ask, given or choosing in any way you like a function s of q, small s of q, is there a as the initial value of capital S, is there a corresponding s at all later times? This is in spirit very similar to the Schrodinger problem. If you know the wave function at time 0, can you solve the Schrodinger equation to get the wave function at all later times? There the answer is yes, if the Hamiltonian is a physically reasonable operator. It has to be Hermitian and so on. Okay. So, here similar question has been looked at, and in a simple minded way one can say, given any initial function little s of q, we believe, we hope, we pray that there will be a solution to this equation starting from that as an initial condition. The initial condition for the Hamilton-Jacobi partial differential equation is not a position and momentum or something like that of a particle. It is a function on the configuration space, because nature of the equation is a partial differential equation. It's not system of ordinary differential equations like Hamilton's equations. Mathematically, it's a very different kind of object. So the solutions of the Hamilton-Jacobi equation should be thought of in this way, in spirit like the Schrodinger wave function problem. Choose a function little s of q on configuration space at an initial time and try to construct the corresponding solution of this equation. This is the spirit. Now, whether it can always be done for all choices of little s, this is, I don't know, a complete set of statements answering this. There are many books on this problem from mathematical point of view. There was a man in South Africa called Hanno Rund. Some of you may have heard of him. Huh? Yeah. He did a lot of work on this in the 50s, 60s, 70s. And he had a student who is very famous these days by name, relativists will know, Lovelock. And in general relativity, in black hole physics or whatever it is, Lovelock's name is quite famous these days, the various solutions or whatever it is. So just imagine these people who are working in Cape Town or Johannesburg or somewhere, quietly isolated from the rest of the world physics community. It was in the 50s, 60s, I remember. So they did a lot of work on Hamilton-Jacobi theory, generalized Hamilton-Jacobi theory, and so on, lot of work. And they have written a couple of books also. So I just give you the name, Hanno Rund. And I think it is James, I don't know. He was, I believe Lovelock was a student of Rund. So Lovelock's name, as I said, is very famous these days in the context of relativity. So we would hope that for each choice of little s of q, we will be able to solve this Hamilton-Jacobi problem and get s of q for later times. Now, there is one delicate thing which comes in here. The Schrodinger wave equation involves a wave function which is a complex function. And yeah, it's a complex wave equation, and the wave function remains complex in general for all times. And we are confident that if the Hamiltonian is physically reasonable, the wave function will always be normalizable. Now, here what can happen is that this is the problem of global versus local description. You may start with a real s of q, but somewhere as time progresses, this capital S may become complex in some places. In this framework, that is meaningless. The classical Hamilton-Jacobi equation, by our agreement, capital S has to be real. So that can run into difficulties. It does not bother you in the quantum case. You may start with a real wave function, and later time it may become complex, no problem. Okay? It can be perfectly well handled by the machinery of quantum mechanics. So that's the kind of thing that I have in mind in telling you that my own understanding of this is a little bit sketchy. If you are interested, you can see more recent papers. It's an active area of research in I don't know what it is called, applied mathematics or it's not mathematical physics really. The generalized Hamilton-Jacobi equations, people write them out just out of general interest, what look like interesting interesting starting point here, making various modifications. Now I come to the last comment I want to make. So let us just imagine in a simple-minded way, you choose little s of q at time 0, t0, and you plug it in here, pull out the solution of the Hamilton-Jacobi equation. Suppose you do that. this solution which you have obtained, let us say you do not face any difficulties in solving the Hamilton-Jacobi equation. Suppose you have succeeded in doing this. It has an interpretation in terms of the trajectories in phase space obeying Hamilton's equations of motion. Now, I have not explicitly said it, but you can imagine in phase space, when you look at Hamilton's equations of motion, ordinary differential equations, we say you choose q and p as you like at a time t0, then the Hamiltonian equations will tell you how the point will move in the course of time, and that is called a trajectory. So, because it is first order dynamics, Hamiltonian equations require only the initial point in phase space, nothing else, and then in principle the trajectory can be completely built up. Okay. Now, so for every point in phase space, any choice of q and p, there will be one trajectory starting from there for a given Hamiltonian system. What is the connection between that picture, individual trajectories in phase space, and the Hamilton-Jacobi equation? Again, it's so beautiful. The recipe is the following. You imagine at t0, you choose any point in configuration space, any point in configuration space, and for that q, you choose your initial momentum in this way. For each position q, you don't choose momentum, initial momentum independently, but by this recipe. So, it means that you are now considering not the most general trajectory in phase space, but those for which at each coordinate q initially, the momentum is somehow determined in terms of q. You don't choose p independently of q. You choose it as given by your initial little function, little s function. Now, with these initial conditions, you will get a trajectory obeying Hamilton's equations of motion, a single trajectory. But how many trajectories do you have here? You have an n-fold infinity of them, one starting at each point in configuration space, and the momentum, initial momentum, determined in terms of it. Here is the nice result. When you take this kind of initial data for Hamilton's equations, imagine solving Hamilton's equations of motion and now ask what happens at a later time. Well, the coordinate will be somewhere, but the momentum, it will be given by the solution of this equation by the same rule. At all times, the momentum is a gradient of the Hamilton-Jacobi function with respect to position. So, this is a way in which the two pictures of motion get connected. So, I can summarize by saying individual solutions of Hamiltonian equations of motion describe individual trajectories in phase space. That is the thing for which you talk about ergodicity, mixing, what was the third thing, chaotic and all that. You are talking of individual trajectories in phase space. Here the focus is different. Every solution of the Hamilton-Jacobi equation describes not one but a bundle of phase space trajectories, but not a bundle put together in some arbitrary way, put together in this very precise way. For every position at the initial time, you choose a momentum by this prescription. This relationship is maintained at all later times through the solution of the Hamilton-Jacobi equation. So, there is a beautiful paper of Dirac in 1951. So, it is long ago, but for me it is in my youth. So, I keep remembering these things. He says, I will give you the reference later. He says that classical, basically I am paraphrasing what he wrote, he said that the basic thing in classical Hamiltonian mechanics is the idea of individual trajectories in phase space. But he says in classical physics, there is classical mechanics, there is a further development. For each solution of the Hamilton-Jacobi equation, we have a family of phase space trajectories built up in a special way. And then he says, we don't understand the significance of these families within Newtonian mechanics. It's not relevant for Newtonian mechanics, he says, but we know that this bundle of trajectories at the classical level somehow corresponds to one wave function obeying the Schrodinger equation in quantum mechanics. Right? See how the connection is built. So he says, therefore, there is some significance to these families, classical level bundles of trajectories, which we do not yet understand. This was 1951, I think. Okay. So I will stop at this. This is to give you a glimpse of Hamilton-Jacobi theory, and this is a nice thing I have been able to complete up to this point. So I want to tell you the only topic which is left, which I want to cover in these lectures, is this Noether's theorem, the connection between continuous symmetries and conservation laws. So I want to conclude these lectures with that topic tomorrow and day after. I don't wish to go into Dirac theory of constraint systems. They are there in the lecture notes in any case in full detail. So it's not good to rush things. So tomorrow and day after I will devote to this Noether's theorem in the classical thing, and I want to show you things which are generally not there even in textbooks. There are aspects which are not discussed in detail. So I also therefore do not need today's tutorial. I have nothing special to offer. I want to start fresh tomorrow with the Noether theorem discussion, tomorrow and day after. So I am willing to donate my tutorial to you, provided you give me a written receipt. Okay, fine. Thank you. We will stop. Yeah, sure.
This family of trajectories.
Yeah.
And then this David Bohm is taking over this. There are some connections perhaps.
I think there could be, because see, in the de Broglie-Bohm approach, the full Schrodinger equation is written in the spirit of the Hamilton-Jacobi equation, but there is some extra non-classical term called the quantum potential. So I suppose you can follow this Dirac's paper and see whether it tells you something. I like that way in which he says the fact that these bundles correspond in some way to individual solutions of the Schrodinger equation tells us that we should go back and understand these things better. Now, I imagine that in the years since then, so much of work has been done on extensions of WKB. What is all this? Gutzwiller and all these people, Maslov index, so many things have been done, which I am not familiar with. Some of these ideas, maybe the understanding has been improved, but I am not familiar with it. Okay. But this is work for you if you are interested. You can go further. Thanks.